In this ShowMe, we're going to introduce quadratic graphs, also known as parabolas. We're going to learn how to graph some parabolas, particularly how to use coefficients to make them narrower or wider, and addition or subtraction to move them up or down along the y-axis. We're also going to explore an application to gravity. First, let's take a look at a parabola. A parabola is a quadratic function in the context we're working here. It's a function because if we apply what we call the vertical line test, notice that a vertical line will only touch the parabola in exactly one place. That means that every single input, every x-coordinate, has only one output, or y-coordinate. That's the sufficient condition that makes a relation, or a set of ordered pairs, into a function. The standard form of the equation of a parabola is y equals ax squared plus bx plus c. The right side is simply a quadratic trinomial written in standard form. The left side is a representation of a dependent variable, a variable that depends on x, which is the independent variable. Y is often also replaced by function notation, which is some letter followed by an x, simply an indication and acknowledgement that the number on that side of the equation depends on the value of x. Parabolas are symmetrical. That is, you can draw a line through a parabola, and the figure on one side of that line will be geometrically congruent to the other side. That line is called the axis of symmetry. We have a special name for the point where the axis of symmetry intersects the parabola itself. We call that point the vertex. If you know the vertex and axis of symmetry of a parabola, you know a lot about it. And if you're dealing with a quadratic function, knowing the vertex is enough to know the axis of symmetry, because the axis of symmetry will be x equals whatever the x-coordinate of the vertex is. These two numbers will always be the same. Quadratic functions are simply vertical parabolas. They can open up, as in the original case that we had on the screen. They can also open down. Either of these will pass the vertical line test. In the left side case, the vertex marks more than just the point where this axis of symmetry intersects the parabola. It also marks the minimum value of the function. Whatever the y-coordinate is of that point will be the minimum of the function. Conversely, in the second parabola, the vertex marks the maximum, because that is the highest value that the function will take on. The y-coordinate of that vertex is the maximum value of the function. Let's consider the shape of this parabola. This parabola actually has a special name. It's called the standard parabola. Its equation is y equals x squared. So every y-coordinate that we see is going to simply be the x-coordinate multiplied by itself. So when we graph the points, 0 squared is 0, 1 squared is 1, 2 squared is 4, and so on. Notice, however, that the parabola, as we said in the previous screen, is symmetrical. That means that those y values are also good for the negative values of x. Negative 1, 1 is a point on the parabola. Negative 2, 4 is a point on the parabola, and so on. Every other parabola's shape is based in some way on the shape of this parabola. Here are the values and another picture of the same graph we had on the previous screen. Now let's consider what happens if we apply a coefficient to the right side of this equation. Instead of having y equals x squared, let's consider what happens when we have y equals 2x squared. Well, the effect of doing that doubles all the y-coordinates. So we need a column that doubles all the values for x squared. So 2 times 0 is 0, 2 times 1 is 2, 2 times 4 is 8, and 2 times 9 is 18. Our new parabola, then, will look like this. Notice that when you double the y values, it has a visual effect of compressing or squeezing the standard parabola into a tighter space. What's really happened is that the points we used to see, for instance 1, 1, have all moved up. In the case of 1, 1, it moved up one place. In the case of 2, 4, which was here, it's now moved up to 2, 8, and so on. But visually, it's a much more comfortable intuition to say that we've compressed the parabola, so it's narrower than it was. It's also very useful to explore what happens when we multiply our right side of our parabola by a coefficient whose absolute value is less than 1. That means that we're going to take all of our y values from the standard parabola and divide them by 4, multiplying them by 1/4. 0 times 1/4 is 0. 1 times 1/4 is 1/4. 4 times 1/4 is 1. And 9 times 1/4 is 2 1/4. That parabola will look like this. Notice that the effect of multiplying all of those y values by a number whose absolute value is less than 1 was to seem to spread the parabola out. What we've actually done, of course, is we've lowered the old points. The point that used to be at 2, 4, for instance, is now represented by 2, 1. We've divided the y-coordinate by 4. Visually, however, it looks like we've spread ourselves out into a wider graph. Finally, for this screen, let's look at what happens when we add something to the right side of the equation. So we're going to graph the parabola y equals x squared plus 3. All we've done is we've added 3 to our y-coordinates. 0 becomes 3, 1 becomes 4, 4 becomes 7, and 9 becomes 12. The effect is simply to translate the graph that you're looking at now to a position 3 units higher. The two graphs you see here are geometrically congruent. The right graph is simply the previous graph elevated 3 units. So whenever we add or subtract something on the right side of this equation, we're simply translating the graph up or down. If we're adding, we're translating up, and if we're subtracting, we're translating down. One last thought before we move into an application. What happens when that coefficient in front of x squared is negative? The effect is to invert the graph, to turn it upside down. Consider our y-coordinates. What we have to do with them now is multiply them by -1, because by putting a negative sign in front of x squared, that's what we've done. -1 times 0 is 0, -1 times 1 is -1, -1 times 4 is -4, and -1 times 9 is -9. All we have to do is graph our new points, and what we're going to have is a mirror image across the x-axis of what we're looking at right now. So whenever you have a negative coefficient, it's going to flip the graph over the x-axis. Remember now, if the absolute value of that coefficient is greater than 1, in other words, if it was -2 or -3, not only would it flip it, it would also compress or squeeze the image visually. And if the absolute value were less than 1, as in the case of y equals -1/3 x squared, that would seem to spread the graph out as it moves the y-coordinates back closer to the x-axis. Remember also that these graphs can be translated vertically too. You could have a graph such as y equals -x squared plus 4. That would look something like this. It'd be the same as the graph I just made, but translated vertically 4 units. Be prepared for all of this when you deal with these parabolas. Now let's consider something of a real-world problem. A bungee jumper dives from a platform. The function h equals -16t squared plus 200 gives her approximate height h in feet after t seconds. Now they didn't say it, but that equation implies some things. If t is 0, the bungee jumper is at a height of 200 feet. I know that because t squared would be 0, -16 times 0 would be 0, and 0 plus 200 is 200. So that means that the platform, even though they didn't tell us, is 200 feet tall. Also, having that -16 there implies that after 1 second, we will have fallen 16 feet, because 1 squared is 1, negative 16 times 1 is negative 16, and negative 16 plus 200 is 184. So we have some pretty basic information just from the equation. What happens 2 seconds into this fall? Well, 2 squared is 4, negative 16 times 4 is negative 64, and negative 64 plus 200 is 136. How about 3 seconds in? 3 squared is 9, negative 16 times 9 is negative 144, and negative 144 plus 200 is 56. We're not going to get to the 4th second before either the bungee characteristics of the cord kick in and we're yanked back upwards, or we hit the ground because the bungee cord is too long. At any rate, these are the relevant values for the function. Notice some things about this. If we graph it, we don't need to worry about negative values. You can't get below the ground, and of course you're bungee jumping. You're rather hoping not to hit the ground in the first place. We identified your top height. Your top height is going to be at the beginning, and it'll be 200 feet. So at time 0, you're 200 feet above the ground. And then we've got the numbers now to track your progress in a vertical direction. After 1 second, you're at 184 feet. After 2 seconds, you're at 136 feet. And after 3 seconds, you're only at 56 feet. So the graph looks something like this. Obviously, at some point, this graph is supposed to violently change direction because you're hooked up to a bungee cord that yanks you away from the planet before you strike it. Some other things to note here. It's not really a parabola because after a while, this function has to stop being the description of what's going on, or your relatives are going to want your money back for the bungee cord trick. They may want a few other things out of the people that set it up. Notice also the graph isn't symmetrical because there is no such thing as negative time. Time begins, as far as this experience is concerned, when you jump off the platform at time 0. So there's no reason to put this side of the parabola in. If you graphed this with t having negative values, it would be symmetrical. But that's not meaningful here because in the real world situation, there is no negative time involved. I hope that helps you understand an application of a parabola moved up or down or inverted. This particular parabola is inverted. This is a fairly accurate model of what goes on with gravity. I also hope you understand that the picture itself doesn't tell the whole story. For instance, this is not the actual path you fall when you're doing your bungee jumping. The bungee jumper will actually simply move vertically. Why does the graph appear to move horizontally? Because time is passing. At different times, you'll have a different picture. But that's not a physical distance that's being traversed to the side. That's a distance along the dimension of time. Still a very useful model that describes accurately how the height changes over time. And this is one very common application of quadratic functions.